Let's start chapter 7.2, which is about volumes of rotation. It's the first of two sections. There's also 7.3 about volumes of rotation. So a big question would be, why should we care about volumes of rotation? Well, it's a good chance to practice one of our big ideas of Calc 2, and we'll remind ourselves of that in a minute. It's a good idea to practice thinking in 3 dimensions. From what I've heard, the real world is 3-dimensional, not just x and y, but x, y, and z in theory. And then it's also the actual procedures here are useful in various physics and engineering classes, such as physics 224, electromagnetism, some stuff in chemistry, like orbitals of electrons you could think of as volumes of rotation. So it does have direct applications to things like that. Let's start out with a little puzzle that's not quite as serious as all that science stuff. How would you compute the volume of this 3D printed object? Got a friend of mine to 3D print this for me. So pause the video while you're thinking about it and then come back. All right, welcome back from pausing. Perhaps you thought of the 3D printed object as kind of a stack of discs, kind of like the stack of a dime, a penny, a nickel, a quarter, and then a quarter, a nickel, a penny, and a dime. So could you compute the volume of each of those little slices and then add them all up? So let's talk about that. Compute the volume of each coin-like slice. Add it all up. That's kind of one of our big ideas of Calc 2, right? To compute a hard problem, turn it into smaller, easy problems, solve each of those, and then add it all up. Coin-like slice we could also call a disk. So what's the volume of the first disk of this 3D printed object? Or you could think, what's the volume of this dime? Well, can we think of that as a cylinder? And what's the formula for volume of a cylinder? It's area of the base times the height. So area of the base is 2 pi times r squared, and the height, we'll just call it h. And this formula actually works for anything where you start with a flat figure and then stretch it out into the 3rd dimension. It doesn't have to be cylindrical. It doesn't have to be circular. The same thing works for a cube. If you start with a square and then stretch it out into the 3rd dimension, you just do the area of that square or even rectangle times how far you stretch it out. So we'll say this works for any flat shape stretched into the hypothetical 3rd dimension. Not just circles. Actually, it's this idea of area of the base multiplied by the height works for any flat shape stretched out into 3D. So what is it for this particular shape? Well, we can measure the diameter quick here. It looks like about 26 to me, so a radius of 13 millimeters. So disk 1, radius of 13 millimeters, height of, we'll call that 5. And then we could go and measure it for disk 2. It looks like a diameter of 42 millimeters, so a radius of 21 millimeters, and a height probably 5 again. Yep. Etc. The point isn't to actually calculate the real volume. Anytime you're doing stuff like this, you might want to make a table out of it. So you could have a table or a spreadsheet. where you'd have like disk number 1, 2, etc. Its radius, so we had 13 millimeters, 21 millimeters. From the radius, you could compute the area by I wrote 2 pi r squared, it's just pi r squared. Lots of people make that mistake, including me. Maybe I'm a person. So then we'll have the area, which would be pi times 13 squared, pi times 21 squared, and then we'll have the height, which was 5 millimeters, then we have the volume of this disk, and whatever, just multiplying those two. And then once we've done all that, add it all up, and we'd get the final total volume. All right, so I'm not saying you should actually go and make this spreadsheet. I'm just saying conceptually you could think of organizing your calculations this way. So that was for this object, which was a lot of fun, but you know what's even more fun than this object is this object. How would you calculate the volume of that? Same basic idea, just kind of twice as much work, right? And if you think that object is fun, you should see this object. It's even more fun than you expect. How would you calculate the volume of this object? So take a sec, think about that, and we'll move on to the next video.